The section that I'm going to review with you guys is 4.8, Analyzing Graphs of Polynomial Functions. The points that I will be reviewing are using x-intercepts to graph polynomial functions, using the local principles to identify zeros of polynomial functions, finding the turning points, and identifying local maximums and local minimums of graphs of polynomial functions, and also identifying even and odd functions. In this concept summary, the function that is displayed is a polynomial function. The following statements are equivalent to this function. For 0, k is the zero of the polynomial function. For factor, x minus k is a factor of the polynomial function f of x. For a solution, k is a solution or root of the polynomial equation f of x equals 0. And for x-intercept, if k is a real number, then k is an x-intercept of the graph of the polynomial function f. The graph of f passes through k0. In example 1, I'm going to be using x-intercepts to graph a polynomial function. The function I'm going to graph is f of x equals to, in parentheses, x minus 2 squared, and in parentheses, x plus 1. The first step that I'm going to do is plot the x-intercept. Because 2 and negative 1 are zeros of f, I'm going to plot the point 2, 0 and the point negative 1, 0. My second step is plotting points between and beyond the x-intercept. The points that I plotted in this table are negative 1, 0, the point 0, 4, the point 1, 2, the point 2, 0, and also the point 3, 4. As you can see, I used the points from the table to graph the function of f of x equals to, in parentheses, x minus 2 squared, and in parentheses, x plus 1. This core concept explains the location principle. If f is a polynomial function, and a and b are two real numbers, such that f of a is less than 0 and f of b is greater than 0, then f has at least one real zero between a and b. In example 2, I'm going to be locating real zeros of a polynomial function. I'm going to want to find the zeros of the function h of x equals to 2x to the third power plus 7x to the second power minus 5x minus 4. My first step, I'm going to use a graphing calculator to make a table. Step 2, I'm going to use the location principle. From the table shown above that I have created, you can see that f of negative 1 is greater than 0 and f of 0 is less than 0. So by the location principle, f has a 0 between negative 1 and 0. Because f is a polynomial function of degree 3, that means it has 3 zeros. The only possible rational zero between negative 1 and 0 is negative 1/2. So the zeros are going to be negative 4, negative 1/2, and 1. And on the next slide, I'm going to have a graph that shows the zeros. On the graph that I have created, you can see that the zeros are negative 4, negative 1/2, and 1. Another important characteristic of graphs of polynomial functions is that they have turning points corresponding to local maximums and minimum values. The y-coordinate of a turning point is a local maximum of the function when the point is higher than all nearby points. The y-coordinate of a turning point is a local minimum of the function when the point is lower than all the nearby points. The turning points of the graph help determine the intervals for which a function is increasing or decreasing. This core concept explains the turning points of polynomial functions. So 1, the graph of every polynomial function of degree n has at most n minus 1 turning points. And 2, if a polynomial function has n distinct real zeros, then its graph has exactly n minus 1 turning points. In example 3, I'm going to be finding the turning points of a function. I'm going to use the graphing calculator to graph the function g of x equals to 2x to the third plus ax to the second minus 3. I'm going to identify the x-intercepts and the points where the local maximums and local minimums occur. I'm going to determine the intervals for which each function is increasing or decreasing. When using the graphing calculator, I was able to determine that the x-intercepts of the graph are x equals to negative 3.90, x equals to negative 0.67, and x equals to 0.57. The local maximum is at negative 2.67, 15.96, and the local minimum is at 0, negative 3. The function is increasing when x is less than negative 2.67 and x is greater than 0, and it's decreasing when negative 2.67 is less than x less than 0. This core concept explains even and odd functions. A function f is an even function when f of negative x equals to f of x for all x in its domain. This means that the graph of an even function is symmetric about the x-axis. A function f is an odd function when f of negative x equals to negative f of x for all x in its domain. The graph of an odd function is symmetric about the origin, and this means that if you rotated it 180 degrees, it's going to be the same. On the bottom left-hand corner is an example of an even function, and the bottom right-hand corner is an example of an odd function. In example 4, which is the last example of the chapter, I am identifying even and odd functions. I will determine if the function is even, odd, or neither. And the function that I will be determining is f of x equals to x to the fourth power plus 3x to the second power minus 2. My first step, I am going to replace x with negative x in the equation for f. Then I will simplify. So the equation will be f of negative x equals to negative x to the fourth power plus 3 negative x to the second power minus 2. Once I simplify that, I will get x to the fourth power plus 3x to the second power minus 2, which is the function that we started with. And because f of negative x equals to f of x, the function is going to be even.